Thanks very much, Tom, and thanks everybody for getting up so early. My task is to make physics seem interesting, which is tricky in 20 minutes, but we're going to see what we can do. Now, how does this guy work here? Click? Oh, this guy here. Okay, got it.
Do you need a...
No, I'm good. So disclosures, and there's a lot of energy sources that can be used, but we're going to be talking about radio frequency energy. The objectives are there. And what we're going to do is to start a little bit on nomenclature. And you see all these words that are up here? I'd like for you never to use them again. I'd like for you never to use them again because the problem is that they reflect inaccurately what we do, what we're using, and how it works. You know, the word bovie is used as a noun and a verb, and as a noun it could be a box or something you hold in your hand, so it doesn't really have any particular meaning. So we have electrosurgical units. You're not cauterizing or boving things, you're trying to create a specific tissue effect. That's what you're trying to do, so that's what you should be thinking and that's what you should describe. We have two electrodes in essentially all radiofrequency electrosurgical procedures, all of them. It's all bipolar. One of them is generally what we call active, and one of them may be active or may not be active depending on what kind of an instrument we have, because we have monopolar instruments that have one pole and bipolar instruments that have two. So there's no such thing as monopolar energy or bipolar energy. They're bipolar or monopolar instruments, and so we're talking about radio frequency electrical energy. So what is this electrosurgery? And what it is really the conversion of electromagnetic energy to kinetic energy to thermal energy within the cell. That's what we're doing. And then we try to translate that energy into the creation of a tissue effect. And there are fundamentally two effects. There's vaporization of tissue, and there's coagulation and desiccation of tissue. It's not cautery. You say, well, wait a minute, what's cautery? Well, cautery is passive transfer of heat. So when you have a match and you touch it to your finger, or if you're a cattle rancher and you brand your cattle, then you are cauterizing. You're passively transferring heat. That's not what you're doing with electrosurgery, except by mistake sometimes. So it's essential that you have a little bit of understanding of physics. And so there's a few high school physics concepts. There's current, voltage, impedance, energy, and power. And current really is just the passage of electrons. Coulomb is a big pile of electrons, and it's the rate at which they go past a given point in the circuit. And voltage is really an electrical potential differential. So you have to create a difference in electrical potential for the flow to occur, otherwise there's no flow. Impedance is and resistance is and direct currents is the term, but impedance is the term we use in alternating currents, and it's really the resistance or impedance to flow, okay? And we'll explain these things. Energy is measured in joules, and it can't be discussed without knowing about power, and power is really the product of voltage and current, and energy is really the amount of this energy that's delivered per unit time. So how do we kind of relate these? There's something called Ohm's law, and that means the current, I, is directly proportional to the voltage and inversely proportional to the impedance. So if you look at this as a water tower, for example, and you have a little spigot there, and you fill your water tower up, and you lift your spigot, you'll have some flow, okay? So the height of the tower is the voltage, the diameter of the spigot is the resistance or impedance, and that little I on the water flowing out of the spigot is your current. Now, how do you get more current? Well, one thing you can do is you can lift your tower higher. And when you do that, you increase your voltage, if you will, with this analogy, and then there'll be more flow. Now, the other thing you can think of is that if I've got that water tower and I ratchet down my spigot, okay, I increase the impedance, I can reduce the amount of water coming out of that tap. All right? Now you say, well, what the hell does this have to do with surgery? And so for example, you have increased impedance with certain types of tissue, like fat, okay, or tissue that's already scarred, or tissue that's already lost its ionic content because you've already desiccated it or coagulated it, all right? So for example, if you've got a vessel going into colon and you desiccate that vessel, and then you want to go and do it again, okay, you've raised the impedance there, right? Ions don't flow through that very well. If you go up there and desiccate it, you're safe. But if instead you go down there, the electrons can't go anywhere else. And so they'll go down to the bowel and create a hole for you. And you might not even see that hole. It just might create an injury, all right? Now, the analogy with the water tower I gave you was one that fits best for direct current or constant polarity circuits. But we aren't dealing with a constant polarity. We're dealing with an alternating polarity. So this water tube analogy actually makes a little more sense. So if I fill this water tube and I tip it this way, okay, then I tip it this way, I'm spinning my little wheel, which will generate power, but the water's really not going anywhere, all right? And so constant polarity, alternating polarity are sort of two different concepts. And with radio frequency, we're dealing with alternating polarity. And what does this mean? It means that 500,000 times a second, we're switching polarity. So if we hook that up to a power generator, you can see as we get to the bottom here, we're going to, without the water moving or flowing in any given direction, we're generating power. So the whole concept of return electrode makes absolutely no sense because electrons are going back and forth. In fact, they're more likely oscillating than they are traveling in a circuit. Okay, so all the circuit diagrams should have arrows going both ways, where the direct current is more like a racetrack. The polarity is constant, and the electrons move around a circle. So now, what does this generator do? What the generator does is it takes the 60 hertz wall circuit, okay, and makes it into 500,000. So 60 gets turned into 500,000 or 500 kilohertz. And the generators do that, but they also allow you to change some elements depending on the sophistication of the generator. And it's important to know that not all generators have the same voltage at a given power, so they do vary quite a bit with these specs and with the sorts of elements that you can modify. So all the generators that you use, and there's a couple of exceptions, but all the ones you use in ORs have isolated circuits. So what's that mean? Well, prior to, say, 1970, that wasn't the case. They were ground referenced, okay? So whereas the isolated circuit has an active electrode, in this case a dispersive electrode, and the patient and the whole electrical circuit is created by the system, in ground reference circuits, all right? In ground reference circuits, the patient was grounded, the machine was grounded, and the circuit was completed through the ground. All right, so what happens there? Well, that means that there's all sorts of things that can go wrong in terms of dispersive current. Current going in two places and through places you don't want it to go through. And in addition, the impedance by the ground required that the voltage had to be much, much, much higher to create the differential so you could have an effect on cells. So you don't use ground reference circuits anymore. You're not using a ground electrode. You're not grounding your patient, okay? So when I hear people say, put on the ground pad, I know they don't understand this stuff. Now, why do we use radio frequency output? Well, it's in this range from about 100 kilohertz to about 3.5 megahertz. And in fact, most of our machines are around 400 or 500 kilohertz. And that's, if you have an AM radio, the far left of your dial, radio frequency. And so what happens? Well, we can control and predict the tissue effects, but the oscillation rate of those ions is such that those calcium and sodium and other channel ions that will not even recognize, so you won't get depolarization. It's too fast for those ions to recognize the switch. So depolarization really doesn't occur for nerves or for muscles. Now, you'll say, wait a minute, why do I get fasciculation? And I can talk to you about that, but basically that's why you don't get it. Now, so let's just try to figure out what's going on in the cell, and we'll start out with this direct current. So if we have an oscilloscope, our current goes in one direction, right? Deflects the oscilloscope one way, like that. So we have this flow. But alternating current, remember, is alternating polarity. So what happens is the oscilloscope goes up and down across zero, all right? Now, it could be a wave like that. More likely, it's a sine wave, all right? So there is no current flow. There's no flow in one direction. It's just oscillating ions. Think of it that way, all right? Now, our generator creates two basic waveforms. It's more than that, but let's think of it as two. The first is the one that you think of as cutting and is labeled cutting on a lot of the US, North American machines, and it's a sine wave, okay? And then if we push the so-called coagulation, and it's misnamed, coagulation waveform, it is a modulated or interrupted waveform with much higher voltage, much higher voltage. So if we look at it here, here's our sine wave that we create, okay? Back and forth across zero, alternating polarity, all right? Now, what's blend? Well, when I started with this, I thought blend was some mix of the coag and the cut. It's not that at all. Blend is just a modulation of the so-called cut waveform. So if we set it at blend, that's what we get. What's on the coag has nothing to do with this, okay? And we have a thing called a duty cycle. So if the wave's on the whole time, with blend, it's modulated. So there's a little less current, and the amount of time that's on we call the duty cycle. The duty cycle, okay? And so if we go, for example, now to the so-called coagulation side, that duty cycle is only about 5, 6%. Okay, so if you think about Ohm's law, at the same power, because you're taking out a lot of the current, the I, you have to compensate for that by increasing the voltage. And that's what's done here. All right? Now, all of the electrosurgery that you do is bipolar. All of it is bipolar. It has to be bipolar. All right? What differentiates the systems is the location and function of the second electrode. So when we talk about monopolar instruments, okay, we have a dispersive electrode, an active electrode. Those are two poles, right? And then we hook those up to different ports on our generator, and our patient completes the circuit when we activate it. Bipolar instruments have both electrodes on them. Okay, so that cable has both wires. And in this example, both electrodes are active. And the only part of the patient involved in the circuit is that between the two electrodes. And that creates some safety benefits. Okay, now to get to the cellular scenario, remember that our normal body temperature is 37. Cell death occurs, or starts to occur, at 50 degrees centigrade, but you need about 6 minutes exposure. At 60 degrees centigrade, you get instant cell death. So when you are desiccating or coagulating tissue, you're roughly working in the 60 to 90 degree, 95 degree range. If you quickly push that cellular temperature up to 100 degrees, the water inside the cell boils. You get a liquid-gas conversion, massive expansion, and vaporization. Okay, to look at this in a cartoon, if we have a direct current and we activate it, the intracellular positively charged particles go to one side of the cell, the negative the other. But that's not what we're doing, right? We are using this alternating current, so we're alternating this back and forth, and these particles and proteins are going back and forth, how fast? 500,000 times a second. So that creates the opportunity to cause frictional change and increased intracellular temperature. So this is how one initiates the cellular effects. There are other features that come in later. Now, so we talked about vaporization, and so if we elevate that temperature to 100 degrees centigrade quickly, we get that liquid-gas conversion and massive cellular expansion and vaporization. But if we keep it in that 60 to 90, 95 range, what we get is loss of intracellular water, damage to the membrane, and shrinkage. So we get shrinkage, so that's desiccation. And then the other thing that happens is we have these proteins in the cell, and we get hydrothermal rupture of those cross-links, and then they quickly reform. So there are two simultaneous processes going on here, desiccation and coagulation. Now, what you're doing with electricity and electrosurgery is really like what this kid's doing in the backyard with a magnifying glass. You're looking for the right focus for what you want to do. So, for example, on the left side, that's what you want a dispersive electrode to do, not focus the energy at all, okay? And the one in the middle is what you're trying to do if you're trying to create a thermal effect. So you're focusing the energy. So if we look at it this way, and we take one of your typical blade electrodes, we're going to try to talk to you about current density or power density. So that's what our focusing is about, and that's the metric that we use. So if we take that simple blade and we put it on its edge, and we take another one and we put it on its side, and we use the same output, cutting current, so-called, that sinusoidal one, we're focusing the energy. But on this one, we're focusing it really highly, and we're going to get vaporization or cutting. And on this one, it's not quite so high. We're going to get desiccation and coagulation. And so this video should show you that same type of a blade. And this is set at 50 watts. And so if we turn it on its edge, we vaporize or cut. When we set it on its side, we activate, and we just get desiccation. And then we can take that same instrument and go back and cut. We haven't changed the output at all. We haven't changed the pedal we're depressing. We haven't changed the button we're pushing. To do this again, if we want to create a tissue effect, if we want to vaporize tissue, we're going to use the so-called cutting current. If we want to desiccate tissue, coagulate, we're using the same output, and we could use the blend. And if we want to fulgurate, which is the first time we've mentioned this word, this is the only time that you need to use the coagulation side. And so we are taking this high voltage and we are trying to control ooze, small caliber vessels, less than 1 millimeter, and that's called fulguration. We'll get to it later. But vaporization, non-contact, desiccation, contact, fulguration is a non-contact process. Now, so if we think of this again, because I'm going through this multiple times to try to make sure you get it, vaporization is basically creating a vapor or steam envelope and then extending it to cut, all right? And it's linear vaporization. And in this particular example, notice how that tissue is desiccated. And what happens here is it vaporizes nicely, but then as you get into this tissue that's already doesn't have many ions on it, it doesn't work, right? So we have to use our scissors to complete the cut here. So one of the big takeaways, I think, from this should be this. I'm going to read it. For optimal tissue desiccation and coagulation, including the formation of a sound vessel seal, coactive coagulation, that's sealing a vessel, should be performed slowly with a low voltage continuous output. That's the cut side, not the coag side. That cut side. Why? All right? So we're going to show you in a few different ways. Here's this high voltage modulated. What happens? You fire a little bit of energy, you desiccate superficially. It's like sizzling a steak. It's like searing a steak. And what happens is you don't get throughput. Your energy doesn't get deep. Your desiccation doesn't become deep. If you use the low voltage continuous, you tend to heat up the entire or a much larger area. All right? So if we look at this process, again, desiccation on a cellular level, on a tissue level, shrinkage on a cellular level from the protein perspective, coagulation, that's our goal. So if we're trying to get a vessel, what do? Well, first of all, we have to compress the vessel, because if we don't compress the vessel, among other things, the vessel will just take the heat away from the site. Even though it looks like it's cooking the outside, it's not going to do anything on the inside. So you have to compress that vessel to prevent the heat sink effect. Okay, and then when you do that, you're going to put one side against the other so that seal can form. Now, If we look at that again, and this is a vessel on its side, this is what you're trying to do. You're trying to get this homogeneous seal. If you use the high voltage modulated, this is what you get. You get this spotty outcome. And you guys know this. You've had a forcep, and then you pull it away. It sticks to the forcep. It separates the vessel. It's all charred and all bubbled, etc. And you've got a vessel that you haven't sealed properly. And that's because you've been using the blue button, if you will. You've been using the coagulation output. So the other thing that happens is that when you do this, you actually elevate the tissue temperature much higher, and you start to break down the organic compounds into sugars. It's called caramelization. That's why it sticks. So when it separates that poor seal with that sort of stickiness. So that's called caramelization. And with Fuse, we made this little animation to show you this. There's what sort of happens on the high voltage side, the modulated side, that spotty seal. And here's what happens if you use the cut side. Here's the more homogeneous seal that's much better. By the way, this is what's used on bipolar devices, this low voltage. The sealing devices are low voltage, just like this. Now, fulguration is really to flash like lightning. It's Latin, and it does have a role. And so what's really great is that it can superficially desiccate tissue. And it doesn't go deep. It doesn't go deep. So you actually, and I'd say this with some trepidation, but you can actually carefully fulgurate on bowel and not go through. Now, I'm not advising you necessarily to do that, but it is self-limited. If you do it properly, it's probably less than 0.5 millimeter. And you do get this sort of sealing by the high impedance. So fulguration, good thing, but that's probably the only reason you need to use the high voltage current or the high voltage output. This is the output that's used in that thing called an argon beam coagulator. It actually does that. And you can cut. You can cut. So those are the objectives that I hope to meet. I'm sorry I had to go so quickly, but I hope at least it got you some idea about what you're doing, why it works, how it works. Thank you very much.
So actually, why don't you stay up here, Mel, for a second?